So, we saw that in linear programming we have constraints which are given in terms of linear functions, and we also have an objective which is another linear function in terms of the variables that we are considering. So, linear means we do not have constraints where I have x1 times x2 or xi squared or anything, right. So, the constraints all involve one variable multiplied by one number, one coefficient. So, that is what linear means. So, I never have variable constraints in which the equation involves variables multiplied by each other. And we saw that this kind of constraint defines these lines which form a convex region, and this feasible region we can then explore the vertices, and this is what simplex does. It starts looking at all the corners in some sense, the vertices of this feasible region, and you are guaranteed that the optimum value, if this feasible region is not empty, there will be some optimum value. It will always be found at one of these vertices. So, it is sufficient to look at the vertices. So, simplex will start at some vertex, evaluate the objective, and if it can find a neighboring vertex which has got a better value of the objective, it will move to that one. So, it is like a search problem along this boundary of this feasible region. So, you start somewhere at one of the corners, look at your neighboring corners. If you can improve, you go. If you cannot improve, you stop. So, it's in that sense it is a greedy algorithm. You can show that this actually works, right. The problem is that computationally, in the worst case, it is exponential, and there are better algorithms that you can use to make it actually polynomial, but it is conceptually very simple, and this is very often used in practice. Then we also saw that when you have an LP linear programming problem with a bunch of constraints and an objective function, you can also take the constraints and multiply it by some constants, right, and make that into a dual problem. And these constants or multipliers that you use, the constraints on those constants, or these are the new variables, right, the multipliers of these equations. The constraints are that these multipliers must be positive, non-negative. They can be 0, but they can't be negative, right. And then when you get, if you solve this dual problem, then you get a solution to the original problem. So, there is this thing of LP duality which is quite powerful. So, now let us look at another aspect of linear programming. So, let us look at a problem which involves planning production, which is similar to last time. We were looking at a sweet shop, and we were looking at what is the production that we must achieve for a given day in the sweet shop. Now, here we are looking at slightly different scenario. So, we have a company that makes hand woven carpets, right, and they have at the beginning of the year 30 employees, and each employee during a month makes 20 carpets and is paid 20,000 rupees. So, since 20 carpets earns him a salary of 20,000 rupees, the labor cost per carpet is 1,000 rupees, right. So, 1,000 into 20 is 20,000. So, this is what it costs to make a carpet. So, now the problem is that we want to meet some demand which varies from month to month. So, we do not always want to make, so if I have 30 employees and I make 20 carpets a month, right, I can make 600 carpets each month, right. But there is a demand which sometimes drops below 600 and sometimes goes above 600, right. So, we must, if let us assume that we know this demand for each month of the year, therefore, we know the demand for January, February and so on. So, there are 12 months, so there are 12 quantities which are known in advance, the demand for January, the demand for February, the demand for March and so on. So, we have these 12 demand quantities, and now we want to somehow adjust our production to meet this demand. Now, there are two problems, right. If I do not have a demand, supposing I am only able to sell 500 carpets in a month, if I make 600, then I have 100 left, right. On the other hand, if I could sell 700 and I make only 600, I am missing out on something. So, I would like to make as many carpets as the demand requires and avoid making surplus perhaps, and certainly avoid not meeting the demand, right. So, we have to cope with this varying demand. So, as a business, what is the option that is available to us? Well, one option is to ask these employees to work more. So, then of course, for overtime, the cost goes up. So, they are paid 20,000 rupees for making carpets and they make 20 carpets a month. So, this works out to 1,000 rupees per carpet, but if they work overtime, you have to pay them more, and how much more? It is 80% more. So, 80% more translates to the fact that this will become 1,800 per carpet, right. For every new carpet they make beyond their stated target of 20, they will be paid 1,800 rupees rather than 1,000 rupees. But there is also a constraint saying that a single worker cannot do more than 30% work over time. That means that if I have made 20 carpets in a month normally, right, then 30% that is 6. So that you cannot make more than 26. So one worker cannot make more than 26 carpets a month, right. So if all your 30 workers were working overtime, right, then each of them will be making 6 extra carpets perhaps, right. So 6 into 30 you can get 180 carpets. So our 600 carpets can now go to a max capacity of 780 if all our employees are paid overtime. But our demand could actually go even beyond that. So then another option is to temporarily employ somebody to make additional carpets. So you can expand your workforce. And of course, when the demand shrinks, you don't need this person, so you can also reduce your workforce by firing somebody. So there is a cost associated with this, right? So there is a cost with finding a new person. So a new person finding costs you, in addition to their salary, it costs you 3,200 just to add somebody to your workforce. It might involve some training and searching and all that. And then getting somebody to leave your company also requires some cost. So perhaps you have to give them a kind of a bonus for hardship and so on. So it costs 4,000 to fire a person. And the third option that we said, when you are going to foresee a demand next month which you don't have the capacity to meet, but this month you have excess capacity, is that you can make extra and keep it. But if you keep it, then you have to store it. So there is a storage cost which is 80 rupees per carpet. Right? So these are all the costs involved. So you have a standard cost for per employee of 20,000 rupees. So if you hire somebody for a month, you pay them 20,000 rupees, they make 20 carpets, right? But if you want them to make more, you have to pay extra. You have to pay another 800 rupees per carpet, but they cannot make more than 6 extra. You can hire and fire people, but that costs money, or you can make extra and store it, and that costs money. So now our target is obviously to find out what is the minimum cost that I will incur if I want to meet this monthly demand exactly for all these 12 months. So my target is to meet the monthly demand and do it with the minimum cost by suitably hiring, firing and storing. Right? So for this I need to know month by month how many people I need to employ. So let Wi be the number of workers whom I employ in a given month. So remember that I started the year with 30 employees, right? So W1, so my I runs from 1 to 12, 1, 2, 3, 4 up to 12, 1 is January, 12 is December. So W0 represents how many workers I had in the month before January, so that is 30, right. Let Xi be the number of carpets that I make in month I. Ideally, I would like to make Di carpets, right. In month I have a demand of I carpets, but I may make less or more, right, depending on how many carpets I have surplus or how many carpets I want to make surplus. So Xi is not always equal to Di. So as we said before, sometimes you cannot meet the demand from your workers' normal workload, so you give them overtime. So we can count the cost of overtime in terms of number of carpets, because we know that each carpet in overtime costs 1,800 rupees. So it's sufficient to count how many carpets were made in overtime. So that is called OI. Right? So we also have this possibility of adding workers and removing workers. So HI will be the number of new workers we hire at the beginning of the month I, and FI will be the number of workers that we get rid of at the beginning of month I. So for instance, we start at the beginning of January, we had 30 employees. Supposing we needed only 27 employees in January, we could have started with F1 equal to 3. That is, we could have fired people at the beginning of January itself. And finally, in order to keep track of this storage cost, right, we need to know what surplus we are carrying. I mean, how much of production we have done which we have not yet sold. So that is the surplus carpets after month I. And if I have a surplus carpet from month I, then in the next month is going to be costing me 80 rupees to store it, right. And of course, I start the year with no inventory, so I can assume that S0 at the beginning of January, that is the end of the previous month, was 0. So I have, in some sense, one of these for every month, right. So I have these 6 variables Wi, Xi, Oi, Hi, Fi and Si for 1 I equal to 1 to 12. So 6 12s are 72, and then I need these two extra variables, as we will see, right, for the month before we started. We need to know what the surplus was coming in. That's a kind of boundary condition. What is the surplus coming into this year and how many workers we had coming into this year. So we have 74 variables in our linear program. So now we have to start expressing these constraints in terms of these variables, right. So the first constraint is, of course, that everything is non-zero and non-negative. I cannot have -5 workers, nor can I hire a negative number of workers, nor can I produce a negative number of carpets, right. So everything here is at least 0. So how many carpets do I make in a month? Well, every worker who is employed will make 20 carpets. So I'll get 20 times WI. If I have WI people on my staff, they are guaranteed to make 20 carpets, no more, no less. And in addition to that, some of them will make carpets because I asked them to do it in overtime. I am not particular about who does it, right. So I will just count cumulatively this value that we have kept track of, OI, as the total overtime contribution to my carpets made, right. So notice that this WI could also change. So it's not that I am sticking to that original 30 employees. I could now have, for instance, 35 employees, as we will see, because of hiring. But whoever is there with me will make 20 carpets, plus some of them will make possibly overtime. So now the number of workers I have will have to be consistent with these three numbers, right. How many workers I had before this month and how many I hired and fired in this month. So this, at the end of the last month, I had WI minus 1 workers, right. This month I hired some and I fired some. So the hired ones add to my worker base and the fired ones get removed from my worker base. So my new worker set is the old workers plus the hirings minus the firings. So this is a constraint which basically tells us how some of these values are connected. It says that these, these three values cannot be completely arbitrary. There must be some consistency between the workers in this month and the workers in next month, and how many people are hired and fired in the next month. Similarly, there is a connection between how much I have surplus and how much I have produced in the last month, right. So if I look at what I had surplus before I started this month, right, so that's how much I had at the end of the last month, right, and I look at how much I make now. So XI is how much I made in this month. So I already had SI minus 1 carpets in storage. I made an additional XI this month, but I also know that I got rid of DI carpets because that was a demand this month. So I removed this from my stock, right. So XI might have been smaller than DI because I am using some old stock, or it could be that XI is bigger than DI because I am keeping some stock to store next time. But whatever excess happens goes into SI, right. So ideally SI minus 1 plus XI should be equal to DI. I have exactly as many carpets as I need to sell, but I could be selling more, right. But remember that everything must be bigger than 0. So SI cannot be a negative number. I cannot be short selling. I mean, I cannot be not meeting the demand. So I must be making at least this many carpets and possibly more with storage and what I made this month, and that will translate as SI, right. And the final thing says that there is a constraint on this 30% limit in terms of production. So though we are not really keeping track of who is producing what, across all the workers, I know that each worker cannot produce more than 6 carpets. So therefore, the total number of carpets that are produced in overtime in a given month cannot be more than 6 times the number of workers who are employed in that month, right. So these are the constraints that I get in terms of these monthly variables. So these are all indexed by I. So there are all these things happen for I equal to 1, I equal to 2 and so on, right. So this is our linear program now. We have this initial constraint which says that W0 and S0, the two which are before this year's counting starts, right. So W0 should be 30, sorry, not 0. So W0 is 30, which says that before I started this year I had 30 workers and I had no surplus, right. And now for I equal to 1 to 12, right, I know that all these 12 into 6, 72 values are not negative. Then I know that the production in a month is equal to the regular production of the WI workers plus the overtime production. I know that the total number of workers respects the total number of workers I had before plus the addition due to hiring and the loss due to firing. I know that the surplus is equal to this month's production plus this month's surplus from the previous month minus this month's demand. And finally, this is our limit of 30% production on overtime. So now the objective function is to minimize the costs. So I have these different costs, right. So this is the salary cost. So the salary cost for the year is 20,000 times the number of workers in each month. So 20,000 times W1 is my salary cost for January, and so 20,000 times W12 is my salary cost for December. Then I have a hiring cost. So for each worker that I hired, remember that we had to pay 3,200 rupees as a fixed cost for employing this person from scratch. So if I just add up the number of workers I've hired across the 12 months, that times 3,200 is my total hiring cost. Similarly, if I add up the number of workers who have been fired across the 12 months, that times 4,000 is my firing cost. Storage costs 80 rupees a month. So if I add up the number of carpets stored at the end of each month during this year, multiply by 80, I get the total storage cost I incurred. And finally, remember that our overtime gives the worker an 80% bonus. So instead of 1,000 rupees per carpet, for every carpet I make in overtime, I have to pay 1,800. So if I add up the total number of carpets made in overtime across the months and I multiply 1,800, I get the extra cost I have paid for employing a worker in overtime. I will do that because sometimes it is better to get a worker in overtime. Supposing I need only 6 extra carpets, it's better to make one worker work overtime rather than hire a new worker who will produce 20 carpets, cost some money to hire, and I'll also end up with 14 carpet surplus, right? So that's why overtime sometimes balances out. So having set all this thing up, right, so we have set up the constraints, we have set up the objective, and as we said before, what we will typically do is run simplex and find a solution. So are we done? Well, in this case, it might turn out that some of the values that we get are fractional. So supposing it says that H3 is equal to 10.6. So H3 is equal to 10.6 says that in March I should hire 10.6 people. Now obviously I cannot hire 10.6 people because people are indivisible, right? I can hire 10 people, I can hire 11 people, I cannot hire 0.6 people. So then we have to deal with this problem where we are expecting integer solutions, but our linear program gives us fractional solutions. So one way to do it is to take a fractional solution which is produced by simplex, right, and try to round it off. So we can say, oh, 10.6 workers, maybe I don't want 10.6 workers. Let me say if I just employ 10 workers, will I meet the demand and what will be the cost? If I took 11 workers, will I meet the demand, what will be the cost, and choose the better one, right? So you can round off your solutions to the nearest integer or to the integers on either side of that fraction and recompute the cost and see. So if your values are very large, right, so if your solutions are things like 1,800 and 1,900 and so on, then you can imagine that, adding plus minus half may not change much to the overall cost. But if your values are small like 10.6, then 10 and 11 can make a huge difference. Remember, 20,000 rupees is what you pay for a worker. So between 10 workers and 11 workers, you end up incurring an extra cost of 20,000 rupees, which might be a large fraction of your overall cost. So if the values are small, you need to be very careful when you're rounding. And in fact, there is actually no good way to do this in general, right? So if we insist that this optimization that we are doing in linear programming must have integer solutions and not arbitrary fractional solutions, then the efficient or non-efficient, even if you use simplex or if you use the efficient ones that we claim exist, they will not work anymore. They will only allow you to solve the problem if you allow arbitrary solutions, including fractions. If you insist on so-called integer solutions, then we get into this problem called integer linear programming, and this turns out to be computationally intractable. So we will see shortly what this means, but computationally intractable really means that there is no clever way to do it. So remember what we said was that there is a feasible region, and in this feasible region, of course, by brute force you can search every combination. So in particular, if you are looking for integer points, you can search every integer combination within that feasible region. So that will give you one way of solving it, but there could be a very large number of such integer points, integer combinations to choose from. But when we say computationally intractable, it really says that some kind of exhaustive search like that is unavoidable in the worst case.